So good morning to everyone. In this work, I present you a cohesive-based model able to simulate the stress propagation along the interface for concrete members retrofitted. The content of this presentation is structured as follows. First of all, I quickly present you the context of the problem, in particular the premature bond failure observed in the field of retrofitting structures. After that, I present you an experimental program aiming to reproduce the phenomenon occurring in the field, so the bond failure. Then I present you a numerical model able to reproduce the stress progress along the interface. This model will be validated according experimental campaign present at the end. In the field...
Vincenzo, sorry, can you move in the full screen mode, please?
Do you see the screen, the full screen now?
No, now. Okay, no problem. Please continue.
Okay. So, it's okay now? Sabrina, it's okay now?
Yes, please.
So, in the field of retrofitted concrete structures, the bond failure on the interface between the substrate and the overlay can be observed after a period of service. The main causes of this failure is due to the different volume change between the overlay and the substrate along the lifespan of the structures and the effects of the external mechanical loading. Overlays in high and ultra high performance fiber reinforced concretes are better suited than ordinary concrete since they provide higher loading bond capacity at the interface. This reduces the risk of premature deterioration. Modeling the bond response of retrofitted concrete members represents a relevant challenge due to the high number of mechanical parameters affecting the phenomenon. Bond response also depends on the field conditions, like the moisture level of the substrate surface prior to the application of the overlay and the fresh properties of the latter. Their effects on the development of bond capacity are still controversial. A few available numerical models able to reproduce this phenomenon are complex for practitioners, which tend to simplify the numerical simulations by using tight interface conditions. Drawbacks of these models is that the bonding failure cannot be directly observed, so the bond performances would be drastically overestimated. So the scope of this work is to develop a simple and effective finite element model able to simulate the stress propagation along the interface of retrofitted concrete members rehabilitated with ultra-performance cementitious mortars. In the experimental programs, I resume the main task carried out from the authors, in particular the realization of concrete substrate. After that, slabs in concrete were cured outdoors for several months in order to simulate the aging of concrete. And then the substrate surface was prepared to the pouring of the overlay, which was a commercial high-performance concrete in a series of this campaign, and in another series was a ultra-performance concrete. The overlay was cured for 20 days, and then the composite members was cut in order to obtain a representative number of specimens to be tested. We can see some figures showing the mechanical testing carried out in order to understand and measure the K-mechanical properties of both single bonded materials, so for substrate and overlays, but also the mechanical properties governing the interface response between substrate and overlay. In particular, The authors designed three kinds of bond testing device, in particular a direct tensile bond test and a direct shear bond test. This kind of tests were adopted in order to calibrate the characteristic of the numerical model. Another kind of test, named the lateral shear bond test, which is able to reproduce the field conditions of the stress propagation along the interface, was used to validate the proposed finite element model. We can also see some pictures about the bond testing device designed by the authors. We can see the main results in terms of stress performance along the interface obtained for both bonded direct tensile test, which reproduce mode 1 along the interface.
Sorry, Vincenzo, can you move on the slide about the results? Because you see your slide number 3 only.
Okay. So you see the slide move on?
Number 3. Number 3.
Okay. Line number 3.
Yes, move. Okay. The slide on the results.
Okay. So.
Okay.
Yeah. That one. I can show you that
yes.
Experimental results were used to calibrate a nonlinear cohesive law, which couples mode 1 with mode 2, and govern the mechanical response of the finite element interface. In order to avoid an overestimation of the bond capacity, the fractal energy magnitude directly measured from the experimental bond test was taken into account. Thanks to that, it was possible to compare the numerical simulations of the stress along the stress evolution along the interface as the external load increases. In particular, figures on the left, we can see the evolution of normal stress and shear stress along the interface as the external load increases. And it is important to note that when in the experimental observation, the crack in the bonding failure starts, in the numerical simulations, this corresponds to the plateau observed in the shear stress evolution. If we integrate the shear stress along the interface obtained by the model, we can directly compare the experimental data with numerical data in terms of evolution of lateral shear load versus slip bonding. In some figures on the right, you can see the main comparison between experimental and numerical data for all experimental series investigated by varying the type of the overlay, so an ultra high performance concrete in one case and an ultra high performance concrete in another case, and also by varying the moisture level conditions adopted on the substrate surface prior to the application of the overlay. We can see that both aspects have played a key role, and the agreement between numerical and experimental data is good.
Only 1 minute to finish, please.
Thank you. We can conclude a simple and effective model has been developed to simulate the propagation stress along the interface of existing concrete structures, rehabilitated with a layer of high and ultra high performance concrete. A family of bond testing device was designed by the author to carefully calibrate the mechanical response of the interface, both in mode 1 and mode 2. The model was validated by a mechanical bond test, which was independent from the test carried out to calibrate the model. Experimental investigation also pointed out that both moisture level of the substrate surface and fresh properties of the overlay stated that the ultra performance concrete are more sensitive to the moisture level than high performance concrete due to their low water cement rating. Limitation of the actual bond testing device designed by the author can be can include the fact that the test device could be longer in order to better reproduce the propagation of stress along the interface of full-scale structures. Thank you for your attention.